So now we've discussed existing concepts in medical physics, let's talk about the frontiers. In this video we will be discussing the workings of proton beam therapy in combating tumours and cancerous cells. We'll start by looking at the workings of existing conventional treatments, and then proceed to see how proton beam therapy aims to improve upon this, as well as looking at the implications of proton beam therapy on our world. A great place to start is with conventional radiotherapy. Radiotherapy uses electromagnetic radiation in the X-ray frequency band, which, as you will have seen in the video on X-ray generation, has a wavelength from 10 nanometers down to 0.01 nanometers, or a frequency of 3 times 10 to the 16 Hz up to 3 times 10 to the 19 Hz. The X-rays are used to target tumours and kill them by depositing energy from the photons onto the atoms in the tumour, thus ionizing them. This ionization causes electron motion to become very erratic, causing instabilities in the molecular structure that upholds the cell. In particular, the structure of the cell's DNA can become greatly damaged, causing DNA strands to split apart. This can result in a process called chromosomal aberration, which is when the cell attempts to repair the damaged DNA but does so incorrectly. This leads to mutations and ultimately the death of the cell. Radiotherapy has been in use now to treat cancer for a relatively long time, dating back to the 1890s, not long after the discovery of X-rays in 1895. However, the use of X-rays actually presents a rather large problem. Photons must travel through the body to get to the tumour and also out the other side if they are not fully absorbed by atoms in the tumour. We can easily see that photons could get absorbed by the healthy cells in the body instead of the tumour. This is what we would call collateral damage, and it causes the deaths of healthy cells, meaning radiotherapy can only be delivered in small doses to prevent large-scale destruction around the tumour. You can imagine if large doses were used, we would not only kill the tumour, but also a multitude of healthy cells that are in the path of the X-rays. We don't want to kill these, we only want to kill the tumour itself. This is where proton beam therapy comes in. Protons do not deposit energy in the same distribution that photons do. Let's take a look at the Bragg curve to understand this in more detail. The Bragg curve shows the average dissipation of energy from a particle over the path length of the beam. The proton has a sharp peak, showing us that the majority of the energy dissipation happens over a short and specific distance. This is called the Bragg peak and is very useful. If we can find a way to position the tumour at the specific path length where the Bragg peak occurs, we can cause the energy dissipation to be greatest within the tumour and relatively low in its surroundings. The Bragg peak actually varies with the energy of the proton, with higher energy protons having peaks further along their path lengths, and drops to zero almost immediately after the peak. This means we would simply need to increase or decrease the energy of a proton beam to get its peak to occur within the tumour. Contrarily, the photon Bragg curve looks far different. It peaks far earlier into the path length and thus far earlier into the body, potentially harming cells close to the surface of the body, and not all tumours are close to the surface. Furthermore, the energy dissipation remains high throughout the whole path, meaning there is a higher chance for healthy cells to be damaged regardless of their position along the path. Constraining the energy dissipation to a small region over the peak would allow us to spare healthy cells along the path of the beam, allowing proton beam therapy to be used in much higher doses. This is one of the biggest advantages proton beam therapy has over conventional radiotherapy. Now let's talk about the maths. As seen earlier, radiotherapy happens in the X-ray band, from around 10 nanometers down to 0.01 nanometer. Using the simple relation that energy is Planck's constant multiplied by the speed of light, divided by the wavelength, this gives us an energy between 100 electron volts and 100 kiloelectron volts. Even the upper limit on this gives us a value far smaller than the energy held by a proton used in proton beam therapy, at 70 to 250 megaelectron volts. This allows protons to collide with and ionize more electrons than conventional radiotherapy. But where does the Bragg peak come from? The formation of the Bragg peak can be understood through the Bethe-Bloch formula, that describes the rate of energy loss of particles as they travel through a medium, such as human tissue. In this formula, we know many important terms such as n, the electron number density, and z, the charge of a particle in multiples of the elementary charge, which for a proton is simply +1. Despite being a very complicated formula, the important part is the beta squared in the denominator. You may have seen this from special relativity, as the fraction of the speed of light that the object is travelling at. This tells us that as the particle slows, the rate of energy loss increases. This may lead you to believe that this is an inverse square law, but in actuality it's not quite. This is because we also have these beta terms. When expanding out the brackets, we can see that the solitary one is simply 1, and the other is within the natural logarithm function, so it grows far slower than the term in the denominator. This means at high velocities, the 1 over beta squared relation dominates, and due to the high energy of the protons, they are travelling at high velocities. As we know the energies and the rest mass, we can actually calculate the velocity of the protons. The energy is very high, which means it would make sense for us to use the relativistic kinetic energy formula, which looks as follows, where m0 is the rest mass and gamma is the Lorentz factor, which is a function of velocity. Rearranging for the velocity gives us an equation that looks like this, so all we need to do now is plug our values in, which gives us a beta between 0.366 and 0.613. Hence the protons are travelling very fast, well within the boundary for relativistic speeds, and thus the 1 over beta squared term will dominate. This ultimately means that after many collisions in the body, a proton will slow down and begin to deposit more and more energy in a confined area, giving us the Bragg peak. This does not occur in the same way for photons as for protons, as their method of interaction is fundamentally different. As you will have seen from the video on X-ray detection, X-rays interact primarily through photoelectric absorption. These interactions are not strongly dependent on the velocity of the photon, which would not vary significantly throughout the human body, and even if it did, there wouldn't be much we can do. In actuality, they are more dependent on the frequency, and since we've restricted ourselves to the X-ray frequency band, we're stuck with the frequency we've got. We don't have the option of using a different frequency, as any lower wouldn't have enough energy to significantly damage the tumour, and any higher would do too much damage to the surrounding tissue. Protons allow us to vary the Bragg peak by changing their energy, which in turn changes their velocity, and can be varied greatly as it doesn't suffer from the problem of damaging surrounding tissue due to their thin Bragg peak. So where do these protons originate, and how do we regulate their energy to get their Bragg peak where we want it? The process starts in a cyclotron. The cyclotron is a machine constructed from charge plates known as Ds due to their shape, and it has a uniform magnetic field perpendicular to them as illustrated in the diagram. A source of protons, for example ionized hydrogen, is placed at the centre of the structure between the charge plates. The proton will of course feel a force moving it towards the negative plate. However, we now have a charged particle moving perpendicular to a magnetic field, and from prior studies you should know that this will of course result in the particle travelling in a circular motion. By connecting a high-frequency AC signal across the plates, we can cause the plates to flip polarity. This will result in the proton accelerating every time it crosses the plates. The increase in angular velocity will of course cause the proton to move in a larger and larger radius of motion until it leaves through an outlet in the side of the cyclotron. However, protons accelerated by the cyclotron often have far too much energy to be suitable for use in cancer treatment, and their Bragg peak would occur far too far into the tissue. To fix this issue, they are first passed through an energy degrader that reduces the average kinetic energy of the proton beam. To do this, the degrader is composed of material that allows protons to interact with it. The protons collide with the electrons in the degrader, causing excitation and ionization to occur. This reduces the energy of the protons to a suitable level. The material the medium is composed of changes depending on the energy loss wanted, but some common materials for proton beam therapy are graphite, beryllium and boron carbide. However, due to the inherently statistical nature of quantum processes and interactions, the amount of energy the proton loses can vary greatly. This can be due to the number of interactions the proton has in the medium, or the amount of energy the proton transfers to the electrons when interacting. For example, a proton exciting an electron would lose less energy than one that purely ionizes it. This results in a large interval of energy for which the protons are in, and as such must be passed through an energy selection process. The diagram simply shows how the energy selection process works. Higher energy protons have their trajectories changed less by the magnetic field than lower energy ones as they are travelling faster. All we need to do is select the width of the exit to be suitable for the energy interval we wish to achieve. The width of the exit is chose based on the depth of the tumour. This is fairly intuitive, as the tumour is not a 2D object. It has a depth, and as such the Bragg peak of the incident protons should vary with its depth. So we simply need to change the width of the exit to the desired width to reach a suitable Bragg peak width, and the protons are ready for treatment. Proton beam therapy is becoming used more and more, with the NHS having 2 centres of their own. Research into how to make proton beam therapy even more effective is currently ongoing, with new ideas and materials for the degrader, and even ideas for multi-layered degrader systems to get the energy of the protons, and thus the position of the Bragg peak, as close to our requirements as possible. It's changing the way we see cancer treatment, and is truly an exciting area of modern medical advancement. Thank you for watching this series of videos. We hope you enjoyed learning about medical physics and the many fascinating concepts it has to offer.